Welcome, everyone. So my name is Nathalie van Hout, and I work at the Belgian Nuclear Research Center. We will talk about radiological impact assessment for wildlife. So very specific radiological impact. So it will be about radionuclides, about radiation, and it will be for wildlife. So not for humans, but for wildlife. So this makes this presentation very specific. So first of all, I would like to start a little bit with the problem setting. So, for example, for nuclear power plants, we have discharge limits that are there for the radionuclides, and they are there to protect people. But we want to know if people are protected. Does it also mean that the environment is protected? Are these discharge limits safe enough, for example? So that is a question that we want to answer, a question that we have. So until now, often was said, if man is protected, the environment is protected, but that's obviously not true because a lot of the organisms are exposed to the radioactivity during their entire life, which makes that they are more at risk, or can be more at risk than humans. So there is definitely need to investigate the effects of these radionuclides on the environment. And there has been already been done a lot of effort to tackle these things. So, for example, we have the UNSCEAR, which is the United Nations Scientific Committee on the Effects of Atomic Radiation, and they form actually the scientific basis that is then used to make recommendations by the ICRP, by the International Atomic Energy Agency, which are then translated into European and national legislation. And this is something, a lot of work has been done on that. So it's very important to take the protection of the environment into consideration. But when we look at the environment, then and this is a difference with when we only look at humans in the environment. You don't have one organism, but you have a whole enchilada of different organisms. And this graph is actually, it's a very old one already, but it gives actually very nice how the different groups of organisms have their specific sensitivity to the radiation. So you can see if you, here you have the different, on the y-axis, you have the different groups of organisms present in the environment. And on the x-axis, you have the acute lethal dose range. So, and this indicates, for example, that mammals, to which we belong, are actually one of the more radiosensitive organisms in the environment. So, and this is, if you compare it, for example, with viruses or bacteria or algae, they are more radio-resistant. And this gives a very interesting mixture of radiosensitivities. And also within a group, for example, within the plants, you already have a big variation in radiation sensitivity. And when you want to protect the environment, you want to protect this whole enchilada of organisms. So we need actually an objective, a science-driven, a science-based benchmark value, which will be a dose or a concentration or a dose rate that is assumed to be safe based on this scientific evidence of exposure and response. So this is in fact very important. So these benchmark values, they give an indication of a dose rate that is considered safe for the environment. And the difference with humans is that for the environment, you want to protect not specifically an individual, because for humans you do protect an individual, but for the environment, you want to protect actually more the population and the ecosystem functioning. So this is a bit the difference between the approaches. And these benchmark values, they are then used by the risk assessors to make decisions, as a value to make decisions. And as said, they have to be derived on the scientific information. So they have to be transparent and science-based. And to do that, or to do the risk assessment of the environment, there is in 2006, there was a European project called the ERICA project that gives a certain approach or a way of how we have to tackle the risk assessment to the environment. So ERICA stands for Environmental Risk from Ionizing Radiation in the Environment, and it was a project to develop this approach, how to tackle the radiation impact on the environment, how to evaluate that. And as said, it was important to look at protecting the populations, the structure, and ecosystem functioning. So not necessarily the individual, not that one fish or that one insect. And the endpoints that are considered, so this is really science-based, and the endpoints considered are morbidity, mortality, and reproductive capacity, because those will define actually your ecosystem functioning. This approach also included the derivation of these screening values. So actually these benchmark values to which you can compare the actual dose of the organism to see if it's safe or not. And these are based on a species sensitivity distribution. So science-based, but that approach, how it's done, I will come back to that later. So as said, it's a very transparent way of approaching this risk assessment, and it's specifically designed to, it's actually a tiered approach, and it's designed to screen out situations of no regulatory concern. But I will also come back to that later. What I want to say with this, together with this ERICA approach of evaluating the risk to the environment, together with that, there is also an ERICA tool, an ERICA assessment tool to do that for non-human biota, and it is that tool that Jordi will explain in the second part of this presentation. So this ERICA tool and this approach, you can also, the ERICA tool, download it from internet. It's freely available. You can use that. So when we then look at the environmental risk assessment, there is a multiple-step screening approach that is then developed. So first is the problem formulation, exposure analysis, the effects analysis, and then the risk characterization. And this figure gives actually the overview of what is being done in such a risk assessment. So first of all, we have the discharges to the environment. Radioactivity gets into the environment, can be in the aquatic environment, can be in the terrestrial environment. And from, for example, the aquatic environment, these radionuclides will be in the water or get in the water. And from the water, they can be taken up by organisms that live in the water, and they cause an internal dose. And when radiation has an effect in the organism, it has an internal dose. So the uptake is through ingestion, through inhalation, not in the water, but for the fish. And then you can have from the water also an external exposure, because a fish will, for example, live in the contaminated water and will be also irradiated from the outside. So you will have an internal and an external dose. And then from the water, the radionuclides can get into the sediments, and these sediments can also externally irradiate your organism. And the same principle can be applied for the terrestrial environment, where you have the radioactivity that is present in the soil. It can cause a direct external dose through exposure, and it can be taken up by the organisms, by plants, and cause an internal dose. And this is add together is summed up, and then we have a total exposure. And then we have to compare this total dose to this benchmark value. And the benchmark value is actually derived by looking at scientific evidence towards the relationship between dose and effects. And when you compare that, when you compare the benchmarks and the external and internal exposure, you can evaluate the risk to the biota. So the first step, so that was the general approach, but the first step that you have to do is actually to formulate your problem. Because when you have a certain scenario, it's important, for example, to first of all, to define the objective of the study. What do you want to do? Has there been a discharge to the environment? And do you want to know whether the environment is at risk? Or are there certain discharge limits already put forward? And do you want to know if they are safe enough also for the environment? So this is really, what is the objective? What is the question from, for example, the government, from the site owner? That's to define the objective of your study. And then you have to look at the time and the space frame. So this means, is it a one-time discharge? Is it related to an accident scenario? Or is it a continuous release over time, for example? How big is the area that is contaminated or that will be contaminated or can potentially be contaminated? And then we have to know something about the source term, about the characteristics. This means which radionuclides are involved, which ones do you expect, what are the characteristics of these radionuclides? Some are maybe more dangerous than others. What will be the speciation? In which form are they present in the environment? Will they precipitate? Will they be very mobile? These are all things that you have to look for and evaluate. And then determining the reference organisms. This means that we have a contaminated environment. There can be a lot of organisms present, but which organisms are there? Which one are most at risk? And then you have to deduce from this group of organisms specific reference organisms that you can use for the assessment, because you're not going to do the assessment for all the individual specific organisms, but you will group them and then look at them as a group and define a reference organism. So there are two things that from this problem formulation, there are two things that I want to show you a little bit more in detail. And the first thing is you have, for example, a discharge into the environment, and then this radioactivity can be dispersed in the environment. It will be spread. It will not stay where it is discharged. And you can model that. And this is also partly included in this ERICA tool, which Jordi will explain later. But for example, for the dispersion, for the environmental transport, there are different types of models that you can use for that. But they have their advantages and disadvantages, but you can go from a very simple box dilution model, a very simple model for which you don't need a lot of information, and it gives you a very general idea of how this radionuclide will be spread in the environment. Or you can go to more sophisticated dispersion models for which you will need a lot of data and site-specific information. So it also depends on, again, your problem definition, which one is more appropriate for your purpose. And one of the coefficients that you will see is a KD, which is a solid-liquid distribution coefficient. And this one is actually the ratio of the activity concentration in a solid phase. Here it is sediment, but can also be soil, and the activity concentration in the liquid phase, which can be here the river water, but it can also be the pore water, for example, when you have it in the soil. And this one is actually a value that is often used in these models, but you will see that it is very specific, it's radionuclide specific, and it is very dependent on the type of the soil or the environment. So it means that you do not always have these values specifically for your site, but you will have to look for them, or for your specific radionuclide, but you have to look for the one that fits your purpose best. And I can already say there is a high variability in these KD values. You will see that. So this is also something it's very much needed in these models, but will also introduce quite some uncertainty, because they can really change orders of magnitude. And then the other thing that I wanted to highlight a little bit are these reference organisms. So in this ERICA tool, we have actually reference organisms which are imaginary entities that are representative for a specific group of organisms with the same dimensions and with the same weight, for example, or similar, so that you do not have to do the evaluation for every single individual or type of species, but that you can group them. And this is also used, so all these organisms are presented as ellipsoids, and it is also used for the dosimetry, because we assume that radioactivity or the radionuclides are homogeneously distributed within these ellipsoids, and that's how these doses are calculated within the tool. So this is an assumption. And these are, for example, the reference organisms that are present in the ERICA tool. I'm not going to read all of them, but also know that if, for example, if you have a specific case where you have very specific organism that needs to be protected, or an organism where you really have to, what you really want to include in your evaluation, and it is not in that list, then you can also in the tool, for example, create your own new organism with certain dimensions and a certain weight, within limitations, but that's possible. And also to take into account that some organisms, that's also something that has to be put into the model or in the approach, that some organisms are, for example, they live a certain period of their life, for example, in the air, and another period, another percentage of their life on the water, or in the water, in the sediment, or so that it's not only in one area that they're present or in one environmental compartment, but that they can be present in different compartments. Okay, and then for the exposure analysis. So first we had problem formulation. We know that radioactivity is present in the environment, in the terrestrial environment or the aquatic environment. And now we want to know or calculate to how much, which dose actually is received by the organisms. And this looks maybe a bit complicated, but I will guide you through it. But as I said, what we want to know is an external exposure and an internal exposure. So an external exposure from external irradiation from the radioactivity that is present in the water or in the soil or in the sediment, and an internal exposure due to the ingestion or inhalation of the contaminants. So these are the two exposures. So, and first of all, as said, we start with the environmental concentrations. And these are the concentrations in the water, the sediment, and soil. And this is the first factor that is present in the equation for a specific medium and for a specific radionuclide, because we look at the different radionuclides separately. And then we want to go from these concentrations in the environment to, for example, to an internal concentration. So for the internal exposure, you need a concentration ratio that gives actually the ratio of the element in the organism compared to the concentration of the element in the media, in the water, or in the soil. And these concentration ratios are also radionuclide specific and organism specific. And these are present in the ERICA tool. So this is to calculate an internal concentration. You have to know how much from the external concentration is taken up by the organism. And for, as I said before, for the external exposure, you need the occupancy factor. How much of his or her lifetime does this organism spend in a certain environment? For example, if you have a bird, you can have external irradiation from the soil, but it will not spend its entire lifetime living on the soil. So that is taken into account. And then you know how much activity is present in an organism and how much activity an organism is externally exposed to. And then you have to convert that into a certain dose. And for that, those conversion factors or coefficients are also present in the ERICA tool because they are also radionuclide and organism specific. And if you sum these two together, you have actually a predicted environmental dose rate. So this is the dose rates that you predict your organism absorbs. And what you want to do, yeah, this is what I said, the occupancy factor, the different habitats. And this is, again, the concentration ratio, but I think that's clear. The thing what I want to tell with this slide is that if you look at a concentration ratio, the whole food chain is implicitly taken into account. So, for example, the concentration ratio for a wolf takes already the uptake through different trophic levels into account. And then we come to the effects analysis. So as I said, what you want to do is compare the dose rate that you obtained in phase 2 with actually a benchmark value in phase 3 to see if you have an effect or a risk. And this is how these, so within the ERICA approach or in the ERICA project, these benchmark values, one value was derived. And as I said, this was done in a science-based, transparent way. So all the information or most of the information that was present at that time for the effects, the radiation effects on organisms was put in a database, and that's called the Frederica database. And from that information, for each organism that we had for which information was available, for each organism, a dose response curve could be put together. Dose response curve I don't know how that works. So on the x-axis, you have the dose rate in micrograms per hour, and on the x-axis, on the y-axis, you have the effect, and then you get a dose response curve. And for each organism, an EDR10 value was derived, so the effective dose rate causing 10% effect. And that was done for a lot of organisms. These EDR10 values were ranked from small to large and put again in a graph where you have again the dose rate on the x-axis. And they were also, each dot represents a certain organism. Then you get again a dose response curve, and then we could derive an HDR5 dose rate in which 5% of the species were affected at this 10% level. And then you get actually a dose rate of 80 micrograms per hour on which a safety factor was applied. And in the end, we get actually this benchmark value of 10 micrograms per hour. So if the dose rate that species are exposed to is less than this 10 micrograms per hour, we can screen out that site from further evaluation. So that is actually what you do then in step 4. That is comparing the dose rate that you obtained from step 2 with the benchmark value of 10 micrograms per hour that you obtained from step 3. And that's what they call the risk quotient. So that's actually just dividing these two values by each other. So the dose rate with the benchmark value. And then when this risk quotient is less than 1, then you can say that your environment is not considered at risk. You can screen out that site. And if your risk quotient is above 1, it does not necessarily mean that your environment or site is at risk, but it gives you an indication that you need to go into more detail. And this is also the whole principle of this graded approach. You start first with a screening with very generic data, with a very conservative approach. And you can already screen out probably a lot of sites that are of no regulatory concern. And for the sites that show that there might be a concern, you go to a more detailed analysis with more site-specific data to look more into detail if there might be a risk or not. So this is all that I had to say. So please, Jordi.
Goedemiddag, good afternoon, buenas tardes. I am Jordi Vives-Ipalle, colleague of Nathalie van Hout. I'm from the Belgian Nuclear Research Center, senior scientist. I'm also professor of the environmental radiation physics for the University of Central Lancashire. And what I do is radioecology, the interaction of radionuclides with the environment. And as indeed Nathalie has said, I will continue this lecture talking about dispersion modeling in the ERICA tool and some practical things about how to use such a thing. As Nathalie has well pointed in her picture that shows the concentrations of radionuclides in the environment, soil, will be water, and that graph that had Nisha show. This assumes that the biota are living where the radioactivity is that they are exposed to. But this radioactivity may come from somewhere else. In a normal assessment, you have concentrations in one place. I start with that, and then you make the assessment for that. But what if the source is far away from the receptors? ERICA has an extra capability to model this. And it's done with dispersion models, which are very simple models that are built into for the screening level calculations, and they're built into the ERICA tool in these tiers 1 and 2 that Natalie has mentioned. These models come from a publication from the International Atomic Energy Agency called Safety Report Series 19, and they are a series of relatively simple, easy-to-use models for various types of ecosystem: freshwater, marine, terrestrial, and they are generic. They are designed to require the minimum number of parameters, and they are designed to be fit for purpose, which means sufficiently complex to be realistic, but sufficiently simple to be practical. A very complex, detailed model may look better in theory, but it requires so many parameters that the uncertainty in the result is just as big as you might with a simple model designed to give a slight overestimate, which is what you want when you're doing an assessment, to ensure that your dose is a slight overestimate and never an underestimate. And this is called conservatism. There's a different meaning in science than in politics. And these models are generally very simple in terms of parameter requirements, and they assume an equilibration between the radioactivity in the water, in the sediments, in the soil, in the different various compartments between which it's distributed. I will go through various types of these models because, I mean, the ERICA tool can be used to do impact assessments. You could also use it to just do dispersion modeling calculations using the atmospheric, the aquatic model, etc. So there are people that use the ERICA tool for convenience because these dispersion models are in there. Others that use them as a part of the ERICA assessment as the first step. The aquatic model is designed to simplify the representation of radionuclide transport in surface water, which depends on a lot of things from diffusion, advection, physicochemical processes that can become very complicated. So this is a simple model in which the discharges of the radionuclides are assumed to be steady and continuous. If you need something with a variable discharge, you need another type of model. The surface waters assume steady state flow, so no turbulent mixing or things like that. The flows, and that's another important thing. For the river model, there is a thing that in here is where the conservatism comes in. When you have a river, and this river, the flow is not constant. There are dry areas, there are years that it rains more, and when it's is full of water, the river gets wider and the flow gets bigger. And when it's very dry, it gets smaller and shallower, and the flow is less. And there are some sets of empirical mathematical formulas that allow you to calculate for a river of a certain width and flow and depth, what is the minimum annual flow over a period of 30 years. Okay, which is for dry conditions. Of course, if the flow is very low, the same amount of radionuclide means bigger concentration because you're dividing by a smaller number if the volume is lower. Okay, so what the first thing you do in these models is to put a flow, and then it tells you it calculates the 30-year low flow rate, and that's important for things that you might be doing later. Okay. And it is assumed that the radionuclides are released along the riverbank, and you can have a riverbank and receptor at the same side of the riverbank or at the opposite side of the riverbank, like in this picture here. And the trick about this is that for a certain distance, if you release on one side of the river, there has not been enough mixing for the contamination to reach to the other side of the river. And this is a parameter in the model that needs to be used. It's a simple analytical model, calculates the concentration in water at a certain distance from this aquatic plume, calculates the sediment concentration using the KV, which Natalie mentioned, which is the ratio of the concentration of radionuclide in sediment divided by the concentration on radionuclide in the surrounding water of this sediment. This is a semi-empirical parameter that is used in ERICA, and it's used in this model. And what you require very few things: discharge rate, river width, the flow, the distance between the source and the receptor, and the location of the receptor. And there are many complex river models that you can use that have all the orography and all the dynamic processes, and that is expensive and complicated and specialistic to use. This type of model I'm showing here is something for when you want a slight overestimate to make a rapid calculation, which is what you require when you do an impact assessment rather than a research study. If you activated the ERICA tool and you went for the choose river model as instead of entering concentrations at that point, you will end with a screen like this, and you enter like in this example, you enter a discharge rate because the input of the model is a discharge rate in becquerels per second. If you have becquerels per cubic meter, this multiplied by the flow rate in cubic meter per second gives you the discharge rate in becquerels per second, just saying. Then you enter the flow rate, the depth, and the width, but there is a button that says estimate, and this estimate is to calculate what the flow rate and the width for the 30-year low minimum of flow, because then it's less width and less flow. So you can either use numbers or ask the ERICA to estimate using these semi-empirical equations that it has. Then we have the lake models and the reservoir models. And this, the easiest way to explain this is by using the bathtub principle. You are in your bathroom, you're taking a bath, and I mean, people who are slightly larger like me always have this spin problem. You fill the bath, you go in, and then the water starts going out through that hole under the tap, and it's very annoying. So what do you do to maintain the volume constant is open the tap until the volume operates constant. And this is the bathtub model. So the small lake of the ERICA tool has this type of model with an input and an output and a balanced volume inside. And it can calculate the dilution of a discharge coming, say, for example, from a nuclear plant releasing into that lake, what concentrations will be maintained when these flows are maintained. So it requires discharge rates, again, inflow and outflow, the volume of the lake, and also the expected duration of this discharge or life of the nuclear facility. And that is a small lake. A small lake is for less than 400 kilometers square. I think it's designed like you see a person standing on the other shore. It's the definition of a small lake. If not, it's a big one. So the large lake is more sophisticated and includes wind flow, the wind blowing on the surface and pushing the water, and some other various things like spatial mixing. But both require a limited amount of parameters: depth, distance between the release point at the lake and the beach, source receptor distance, and the current velocity, because there is a current, surface current in such a lake. That's the other model. Then we have the atmospheric model. I think that's more conventional, and some of you may be familiar with the Gaussian plume dispersion model for atmospheric dispersion. It's a model in which you have a chimney, and there is a material coming out from the smokestack, and then it disperses using a Gaussian E2 minus X square type of dispersion equation, which also factorizes the wind direction and the wind speed and the weather and factors of this kind. But this model is very conventional and classical, but be careful because it applies between 100 meters and 200 kilometers of the chimney, no more. I've seen many assessments by national regulatory bodies abroad, I must say, that applied it for distances of several thousand kilometers and gave completely wrong answers. These models that are approximative tend to be for a certain range of applicability. And this, in here, again, you put the discharge rate of the radionuclides, the duration of the discharge. There is dry and wet deposition coefficients because they also include the rain, if the rain is washing out some of this plume onto the ground, or the dry deposition of the dust particles, distance to the receptor, and they even have building effects. If there is a building between the chimney and you, the air current goes a certain way, and it includes, depending on the dimensions of that building, it makes a slightly more sophisticated type of calculations. And this is a typical example of what it would look in the ERICA tool. And you put here, I put a discharge of tritium, because tritium is what comes more out of a nuclear power plant stack. It's the main thing coming out from a chimney in any reactor. And this is, along with the noble gases, you put the discharge rate in becquerels per second, and the release height, the distance to the receptor, wind speed, the fraction of time the person is standing in where the wind is blowing, because this is called an occupancy factor, the position coefficients. Where there is a star, it means ERICA uses a default value, and various other things. And then you can come out with those assessment, because the ERICA calculates then the concentration where the animal is standing, say, and from there continues running the rest of ERICA to arrive to the dose assessment. So these models are fully integrated, although you can also run them standalone. And for coasts and estuaries, for a coastal water, it uses the large lake model, but it's only valid for less than 100 kilometers from the discharge point. So some people I have seen using this to calculate the spread of the plume of Fukushima over the Pacific Ocean all the way to the United States. No, for that you need a global circulation model. For estuaries, which is when the river reaches the sea, and therefore there is a salinity interface where there is brackish water, you can use the river model with adjustments for the tides, because there is tides coming in and out, and there is the phenomenon of tidal rectification in an estuarine environment. Also, you're familiar with oceanography. No, this has to be taken into account because it restricts the outflow of the water. And again, it requires simple parameters like discharge rates and depth and width, flow rate, the tidal periodicity, and location of the source receptor, etc. So these models are quite since the ERICA tool is free and you can download it, just type ERICA assessment tool and it will be into a site. It's run by Facilia in Sweden. It's free, but you have to register, but you don't pay anything. You can get for free these models by downloading this ERICA tool. So this is all I wanted to say about the dispersion models. And now a few very practical slides about how does the ERICA look when you try to make it run, and what are the basic operations that you can do and how. When you, and sorry for the misspelling of organisms, when you get the ERICA tool activated, after an initial set of screens that you use to describe the assessment, put your name and describe, there is a series of screens because it makes a report in the end, so you can do it all in there. You arrive to the first practical screen, which has a list of radionuclides, 88 radionuclides to cover all the expected ERICA environmental risk assessment scenarios like norm, routine release, post-accidental, and waste repositories. And you have these in the left-hand side in the column listed in alphabetical order, and you keep selecting them for the radionuclides that you want to do the assessment for. But sometimes there are exotic isotopes that are very strange and they're not common to assessments that are not there in this screen. However, ERICA allows you to select them by creating them. An example, say you want to do lutetium-177, one of these strange medical isotopes that have very short half-lives and they are not in the list. You set add isotope, and ERICA has the relevant ICRP and data tables, decay tables, and everything to fish them back. The reason you have to fish them back is that if you put all the radionuclides in this menu, it will be a huge file and it will be too large to put in a computer. So it just gives a selection and then you add the other. Then you select marine, terrestrial, or assessment, or freshwater to see what type of assessment you have. And at that point, you can select the reference organisms, which are on the second column, and that they are Natalie indicated in that slide that had a very long list for the environments. Then you can run this as a single point, which is why you normally run it. But you could run it as a series of data for different locations, or as a temporal series of data for one given location if you have tables for different years and all this, so that ERICA crunches all the numbers without you having to make one assessment for every one of these cases. But normally we use it in single point. Then you select the screening value of 10 microarrays per hour. Then you select the uncertainty factors, which are usually just leave at default. And whether you use site-specific media concentration, which means the normal case, you have so many becquerels per liter in this lake, how much the fish you are going to get, or use the IAS-RS19 model if the source and the recipient are in a different location, which I have already explained. And then this has various levels, from simple to complex, requiring less data to more data, as Natalie exactly explained. The tier 1 is a highly conservative type of assessment where you have minimal data input, and it gives a thing called the maximum measured or estimated media concentrations, EMCLs, environmental media concentration levels, are programmed in the tool. What is an EMCL? I'll tell you in a moment. Environmental media concentration limits. This is basically the first organism to hit 10 microgray per hour for a given radioactivity concentrations. It tells you which is, if you select all organisms, which one would be the first one to hit the 10 microgray per hour. And so it's a kind of a more restrictive thing. If everything is below the MCLs, it simply says you passed the assessment, okay? And then you can go to you can say, thank you very much. This site can be excluded from consideration or further study because at tier 1, we have passed the assessment. Also, we wanted, because I was involved in the design of this thing, and we thought this would avoid a lot of work. Unfortunately, the governments and the nuclear plants and the operators, they all require the full detailed tier 2 assessment. So this is not so used in the way it should have been, because it would save a lot of work. If everything passes at tier 1, it will pass also tier 2 and tier 3, obviously. What you cannot have is something that passes tier 1 and fails tier 2, because then it would say that when you restrict more the assessment, we're contradicting the hypothesis, the conservatism of the first pass. And when I was in this project, there was a coordinator, was Carl Magnus Larsson from Sweden, and he had a bottle of aquavit to present to the person that made an assessment with Erica that passed tier 1 but failed tier 2. And nobody got the bottle. I mean, that's as simple as that. So then we can exit the situation. However, if we crack an NEMCL, if we reach to a point where at least one of the species considered reached the 10 microgray per hour, it says, let's now look at it more seriously. And then comes the tier 2. The tier 2, which is most generally used, reduced conservatism. Here you can start manipulating parameters, because in tier 1, the parameters are set in the ERICA tool. That means that, for example, if I have concentration factors or KVs that are more realistic than the default values for ERICA, because the default values for ERICA are designed to be on the upper, more conservative level, because I've made measurements in the site and all this, then I can make a less conservative assessment. And this is what happens. If you fail tier 1, you'll take measurements, you measure concentration factors, you measure KVs, you may even measure biota activities in the water, and say, okay, with more realistic values that are site-specific, how does the assessment look? And it has a traffic light system indicating the situation is of negligible concern. If it's green, exit the assessment. Of potential concern when you are close to this screening value of 10 micrograys per hour, or of more concern, in this case, you should continue the work. And tier 3, which we will not describe because it's very seldom used, is a probabilistic retrospective evaluation of the site. Basically, the bottom line is maybe my assessment, I exceed the 10 microgray per hour, but the probability of exceeding it is in maybe less than 5% of the situations. Because you can put probability distributions for the key parameters, KVs, concentration factors, in there to calculate this. That could tell you that even if you fail tier 2, 95%, for example, of the biota would not receive the maximum dose. That tells you again if you can pass the assessment at that level. So, as I said, when you start the assessment, you first document the process. We were a bit naive here because we thought there'll be an end to all these long reports, because people will document this in the tool, and you'll just have to send to the government the ERICA file but no, they still want the long reports and everything else. But you can document things here, what tier you are in, Do you need to engage stakeholders? No, for the people vested in social sciences, and that they have considerations about, we have to consult about these results. Formulation of the problem, description of the assessment, etc. After that comes the data entry. At tiers 1 and 2, you can either enter empirical data, like concentrations of in water for the various radionuclides or in soil, or you can enter model predictions. A model has been used to predict those concentrations from a source that is situated far away, or at ERICA to use its own models. And then at tier 3, you have more detailed type of inputs with distributions of probabilities for the parameters. This slide is very dull, and it always gets stuck when I give it. But it's about the definition of the EMCL for tier 1. It's basically it's saying F is the dose rate that a given organism can receive for a unit concentration of radionuclide, and the predicted no effect dose rate divided by this gives you the EMCL. It's a trigger to pass or fail, and that depends on the organisms and the radionuclides considered. And these are EMCLs calculated for different biotas in different environments. If you want to calculate, do it by hand. Say, okay, the EMCL for carbon-14 is 84. So therefore, if your concentration is bigger than that concentration, then you already know you're going to fail tier 1. Otherwise, let ERICA do it for you. Then we have the risk assessment. We have a risk quotient defined by in tier 1. It's a bit different from the Natalie definition for of risk quotient. It's the measured activity concentration divided by the MCL. And if that's bigger than 1, the ERICA tool tier 1 says, boom, you failed the tier 1. And I forgot to say, the risk quotient is assumed for all the individual radionuclides to give the overall risk quotient of the mixture. It is a bit like copied from toxicity, from additivity in concentration addition in ecotoxicology, to give you that overall ratio. Okay, then in tier 1, you select radionuclides, and like in here, and you can select your predicted no effects dose rate as we do in all the other tiers. And then it automatically, you put in the concentrations of radionuclides in the water for the different isotopes, or soil if it's a terrestrial assessment. And then, boom, it comes out with this thing that tells you for each isotope, which species has failed the tier 1. And that would indicate I cannot stop at tier 1. I have to get into more detail on the problem. Tier 2, here, it's the endpoint is not these ratios, these AMCLs. It's the dose rates in the reference organisms. This is making the real assessment to all the way to calculate those rates. And by the way, those rates in humans are usually in sievert per year. And sievert, as you know, is a calculation that takes into account the effect of radiation, biological effect of radiation with the radiation weighting factors. In ERICA, you do it in grays per year, and in fact, you do it in micrograys per hour, based on because it's the number that has less zeros in general when you do assessment. So you use a convenient unit. You always see them in micrograys per hour. And in tier 2, you can see how the concentration ratios are derived, and change them if you have some of yours, and inspect the various occupancy factors described by Natalie for the occupation in different parts of the environment, etc. The ERICA tool has a database of concentration factors, and this database doesn't have values for all radionuclides. These concentration factors or concentration ratios, by the way, are for elements, not for isotope, because different isotopes of the same element will have the same concentration factor, because it's a chemical and biological thing. It's not a physical thing. In general, you will have gaps, unless you choose the most common radionuclides in organisms, like cesium and fish. But Erica has a method to fill the missing gaps. It's done by a series of interpolations and extrapolations, but using a variety of methods. And you see in the right, for example, similar taxonomy. If I have the concentration factor for a lizard, but I don't have it for a bird, it assumes that, okay, birds are also descended from reptiles, so let's use the same concentration factor. It's a bit brutal, but it does tend to work in practical terms, and it tends to be conservative. Or you can see that is a similar radionuclide. For example, if you want, let me see, the concentration factor for barium is missing, but you have the one for radium. Well, these are neighbors in the periodic table in the same column, so it will extrapolate to a similar chemically behaving radionuclide, because the concentration factor, as I said, depends on the biology. So there is always a biological analog, or on the chemistry, and then there is a chemical analog. If you press all these various buttons, you can fill the table like this, and then Erica will only allow you to continue when the table is filled. Now, the risk assessment is based on the basis of the Nathalie risk quotient, which is basically the dose rate divided by the predicted no effects dose rate, which is the 10 microrate per hour. So the dose rate calculated by your tool divided by 10 microrads per hour is a number. If this number is, and then when you assume for all radionuclides, if it's less than 1, you've passed the assessment. If not, you have to do more study. And then also there is a thing called the conservative risk quotient and the non-conservative, which is the 1 multiplied by 3. So if the assessment says your conservative risk quotient is less than 1, green light. If it says your conservative risk quotient is less than 1, but the non-conservative one, which is 3 times more, is bigger than 1, you're orange. And if you exceed the 2, you're red. It's a pass or fail mechanism. This is just exactly what I said. Okay. And also this, that's the graphical version of what I have explained. Because there are cases that are borderline, which is when you are between the conservative risk quotient and the other one. And that allows you to make decisions about whether you need to investigate more about this site, maybe take more measurements to make sure that you're doing the assessment realistically as possible. So in tier 2, you start again with the list of radionuclides, you select them, the organisms, you select them, just like in tier 1. But now it goes to a screen of distribution coefficients, which are from Erica's database. They are in there, but you can change them if you don't like them. These distribution coefficients come from the IAEA handbook of parameter values. It's an IAEA publication, but you may have a better measurement for your site, and you can put them manually, and it will then change the color to blue. I think it is when you do that. Then here there are the occupancy factors in the next tablet. For example, it's a very simple system. Say there is a frog that spends half of the time swimming and half of the time standing on the shore. Then the occupancy factor on soil will be 0.5. The occupancy factor in water will be 0.5, and the occupational factor for in the bottom of the water will be 0. So you classify them all in this way. And then you enter your concentrations, and this is how it would look in Erica tool. You can enter concentrations in the water, for example, in aquatic, or in the soil, or terrestrial. But if you don't have some of them, but you have measurements directly on the animal, you can also enter in becquerels per kilo in the fish or in the amphibian there. Provided Erica has a combination of the two, it will allow you to do the assessment. Because to calculate the concentration in the animal, it will multiply the concentration of the water by the concentration factor. Likewise, if you count the concentration in the animal, you can get the concentration in the water by dividing by the concentration factor. So provided you can go in both directions, assessment can continue. And then you get the result. And in the result, you have this traffic light thing that I've measured, and it tells you the risk quotients that were expected and for conservative. And from here, you go to your conclusions. The tier 3, sorry. I think we are near the end, no? Yeah, we're near the end. The tier 3 is a probabilistic thing, and here I'm not going to go in details because you're not going to use it very often, but you enter probability distributions of parameters. And for the rest, is quite similar, except that now you enter different probabilities. You can use a Gaussian, binomial, square, triangular, various types of distributions. The occupancy factors, the concentrations, and now you get the output as a probability distribution. But for those who like probabilistic analysis, you can run a tier 3 for many things, including those. And the last two slides. The final reflection is that the ERICA tool makes many assumptions and simplifications. The geometry of the biota is simplified using ellipsoids, assumes homogeneous distributions. Only a few organisms with simple geometry can be defined. It does size interpolations with certain ranges. And there are some things that ERICA cannot do. Limitation on which reference organisms appear under which ecosystems. You cannot calculate those coefficients for marine birds in air, for example, because of this. The plant geometries are unrealistic, and for this you need more advanced models, which we are developing at SCK, because a plant is not an ellipsoid, it's a fractal. A tree is a fractal, basically, for a mathematician. So that's where the method would fail a bit on the dosimetry. And also what part is above ground and below ground, this is complex to describe. And that's it. I hope that we've been able to give a brief, quick introduction. I advise you to play with the tool, download it if you want to use it, and then God knows where you might find the use for it in the next few days. I will have to figure that one out. Thank you so much for your attention.